Assalamu alaikum wa rahmatullah. Welcome to another session of EEE 4535. So in the last class, we were discussing about the issues, some of the issues associated with the emission. And we presented some statistics related to the harmful effects of greenhouse gases or fossil fuels consumption on human health and overall on the environment. Specifically, we talked about the global warming scenario, the carbon dioxide emission by region, and overall the greenhouse gas emission scenario from the year 2019. We talked a little bit about the acid rain, the definition of acid rain, how it actually is produced due to our daily life activities, both through the transportation section and also the industrial activities. And we presented the data on the amount of the percentage amount or the exact number of people who are suffering from the unsafe drinking water. And finally, we presented a comparative assessment among different energy resources. So today we will start, we'll continue with the emission consideration. We start with the idea of the carbon footprint. So the definition of carbon footprint says that whatever activities we are doing in our daily lives, starting from our household activities, consider our office activities, we are commuting from our home to the offices, and then the industries, they are going through their own activities of producing and manufacturing plants are running. So every people through his or her activities are actually, every people is actually emitting some amount of carbon or greenhouse gas in the environment. So the carbon footprint is solely related with the carbon dioxide emission. So it doesn't consider all the GHG emissions. So not all GHG emissions are considered here in the carbon footprint. Rather, only the carbon dioxide emission is taken into consideration. So through our acts, we produce some amount of carbon dioxide that goes into the environment. So now for each kind of fossil fuel, this amount varies, of course. So if we look at the data, some of the relevant carbon footprint of some of the major or most popular fossil fuels, like the natural gas, its carbon footprint is 11.2 pounds per cubic feet. So CFT stands for cubic feet. For fuel oil, which is also named as diesel, it releases 22.37 pounds per gallon. Means if we burn 1 gallon of diesel, it will emit 22.37 pounds of carbon dioxide into the environment. Similarly, the propane, another fuel, it releases 12.17 pounds when 1 gallon of propane is burned. And considering electricity generation, different kinds of power plant utilizes different kinds of fuels. And some of them may have a mixture of fuels. Instead of a single fuel, they may go for the mixture of the fuel. So in those cases, this value, which is presented here, will vary. Of course, this is some averaged value. So 1.5 pounds per kilowatt hour. That means if the power plant produces 1 unit of energy, where the unit of energy is represented by kilowatt hour unit. So for producing 1 kilowatt hour, the power plant emits 1.5 pounds of carbon dioxide on an average. And similarly, if we burn petrol, if we use petrol, so then in that case, you can see that the value is pretty high. It's 20 pounds per gallon. So these are some of the values taken and shown here. So from this, we can have some idea that which of these fossil fuels emits larger amount of carbon and thus have larger carbon footprint, and which one produces less amount of carbon and have a smaller footprint. So now if we solve some example problems, very small example problems, just to make us familiarize with the calculation of carbon footprint, because when we talk about emission in the environment, and if we are trying to set up a policy, appropriate policy for reducing that carbon emission in the environment. So in that case, first of all, the first step is, of course, to find out how much emission is actually being created by me, or by a certain household, or by a certain industry, or by a certain office, whatever we say. So considering that, let us go through a few examples. So this is the first example, which states that the average home in the United States, it uses about 11,000 kilowatt hours per year. So that is actually its electricity consumption. Per year, electricity consumption, 11,000 units. So they're asking for the determination of the carbon footprint, okay, electricity-based carbon footprint of the average house in tons in the United States. So this is, of course, a data of a certain year. From for another year, maybe this data will vary. So for that year, we need to determine how much carbon footprint was there. The value is there given for the carbon emission per kilowatt hour. So this is the carbon footprint for the electricity production or electricity generation. So 1.5 pounds of carbon dioxide will be emitted for per unit energy production by the power plant. So here the solution starts. So we have this many houses in the US. Again, this is some data taken from some statistics. So 115,000,000,000, these number of households are there in the US. So what is the total electricity-based carbon footprint of US households in tons? So basically, this is continuation of the question. Sorry, this is the continuation of the question, and here the solution will start. So now the another question. So for the first question is, what is the electricity-based carbon footprint of the average home? And then they are asking for the determination of total electricity-based carbon footprint of US households in tons. So here the solution starts. Basically, we have 11,000 kilowatt hours consumption per year per household. So this is the average home. That means for a single year, for a single home, average home means for any home, for any single home in the US. So this is the average yearly consumption per home. So this is 11,000 kilowatt hours per year per households. And then we know that for producing 1 kilowatt hour of energy, the power plant emits 1.5 pounds of carbon dioxide. So we have 1.5 pounds of carbon dioxide per kilowatt hour. So if we calculate this, then kilowatt hours and kilowatt hours gets cancelled out. We are left with this value 11,000 into 1.5 pounds of carbon dioxide per year per household. So after calculation, we get 16,500 pounds of carbon dioxide per year per households. So this is what we get from this. Now we need to know in tons. So this is in pounds. So we need to know in tons. The question is asked for the calculation of the tons of carbon dioxide. So that means we have to convert this pound into tons. We know this is the conversion factor from ton to pounds. So 1 ton equals 2,000 pounds. So if we multiply it with this, then this pound gets cancelled and we are left with this many 16,500 divided by 2,000, this many tons of carbon dioxide per household per year. So this is the answer for the first question. So you can clearly see that throughout the year, if this is the average consumption, then throughout the year, one house will emit or is emitting 8.25 tons of carbon dioxide. Or in pounds, I can say 8.25 multiplied by 2,000 pounds of carbon dioxide is emitted by a household in the US on an average. So what will be the total carbon footprint of US households? We're talking about households. This is not industry or other offices. This is the household activities, considering the household activities. So we have 8.25 tons of carbon dioxide per year per households multiplied by the number of households. Simple. So the number of households gets cancelled out, and then we multiply this value with this value. So this is the result, 948,750,000 tons of carbon dioxide per year. If we convert it into metric tons or millions of tons, then it becomes 948.75 million tons carbon dioxide per year. So this is the carbon footprint, means this much carbon gets emitted from the household activities of United States for that specific year. Okay. So let's move on with the next example. This was one of the examples. So let's move on with the next example. We have the second example. Here it says that you have a large commercial natural gas furnace. So you have a gas furnace, commercial gas furnace. So this is our gas furnace, which burns 10,000 cubic feet of natural gas in an 85% efficient furnace. So the furnace efficiency is 85%. That means whatever fuel it takes, whatever energy is produced by the fuel intake, only 85% of it actually comes out as the output. So it burns 10,000 cubic feet. So, and the question is, how many tons of carbon dioxide gets emitted? So we are looking for CO2 output here. And then we have another question. It says, it also asks for how much heat is emitted. Of course, the job of the furnace is not to release the carbon dioxide. This is a byproduct of the process. So the actual job is to produce the heat. So it takes the natural gas, burns it, and produces heat. So how much heat is emitted? This is the question. And along with the heat, how many tons of carbon dioxide gets emitted because of the usage of the natural gas as the fuel for the gas furnace. And another value is given, which is 11.2 pounds of carbon dioxide per cubic feet. This is the carbon footprint for natural gas. Again, it means that if I burn 1 cubic feet of natural gas, then it will emit 11.2 pounds of carbon dioxide. So let's start the solution. We have 10,000 cubic feet. This much cubic feet of natural gas gets burned. So this much cubic feet, if 1 cubic feet of natural gas produces 11.2 pounds of carbon dioxide, then 10,000 cubic feet will produce 10,000 into 11.2 pounds of carbon dioxide. So this will give me the value of carbon dioxide in pounds. I need to get the value in tons. So again, I use the conversion factor of 1 upon 2000. So 1 ton is equivalent to 2000 pounds. So for converting the pounds into tons, I multiply it by 1 upon 2000. So I get 56 tons of carbon dioxide. So by burning 10,000 cubic feet of natural gas, basically we are producing 56 tons of carbon dioxide. So this is 56 tons. Now, the next question is how much heat is emitted? So as we know the efficiency of this furnace, gas furnace. So if we can find out how much input heat is given, then because we know the efficiency of the furnace, we can easily calculate the output heat. So let's try and calculate the input heat to the gas furnace first. And that input heat will be, of course, created due to the burning of this 10,000 CFT of Ng. So Ng input, natural gas input is 10,000 CFT, which will, of course, which will be converted into heat input. So how much heat input is there? So let's calculate the input heat. 10,000 CFT is the natural gas. And this value is again taken from the standard data, which says that when you burn 1 cubic feet of natural gas, so burning 1 cubic feet of natural gas, if you burn it, that produces 103.000 British thermal unit. This is another unit of representing the heat. Okay, like we know, there are other units of heat maybe there. So this is the British unit, British thermal unit. So 10,000. So when we burn 1 cubic feet, we produce 103,000 British thermal unit heat. So if we burn 10,000 CFT, how much heat will be produced? Simply we can calculate it by multiplying this. So the value comes out as 1.03 multiplied by 10 to the power 9 British thermal unit. And the output heat, so this is the input heat. This is the input. And the output heat is simply the input heat multiplied by the efficiency. The efficiency is given as 85%. So we multiply this input heat. So this natural gas, when you burn it, it produces heat input. So we are looking for output heat. So input heat multiplied by the efficiency is 0.85. Then we get 875.5. Again, this is converted into millions of BTU or 10 multiplied by 10 to the power 6. You can also say 875.5 multiplied by 10 to the power 6 BTU. So this much heat is emitted along with this much carbon dioxide. So this is the second example of carbon footprint calculation. Let's move on with another example. Let me erase these texts markings. So this is another small example. Let's go through it very quickly. So we have now an example of a single apartment where we have only 100 people living in it. and they are consuming 1,000,000 kilowatt hour of electricity. So what is the carbon footprint of the building in tons of carbon dioxide per cap? Here the cap actually means per capita or per person. So this is nothing but cap means basically capita or a single person. So again, so we have this value given, so 1.5 pounds of carbon dioxide per kilowatt hour consumption or production of electricity. So it's very simple, straightforward. We have basically here we have 10 to the power 6 kilowatts hour of electricity being consumed or used up by the apartment people, 100 people. So first we convert this value into pounds. So this is given, sorry, we convert this value into equivalent. Yeah, equivalent. So from kilowatt hour, we convert it to equivalent pounds of carbon dioxide by multiplying it to 1.5. So kilowatt hour gets cancelled out. We have 1.5 into 10 to the power 6 pounds of carbon dioxide. Then we convert the pound into tons by multiplying it by this factor, 1 upon 2000. So then pounds and pounds gets cancelled out. We have 1.5 into 10 to the power 6 divided by 2000 tons of carbon dioxide. This value will be the total tons of carbon dioxide emission made by these 100 people living in the apartment building. But we are looking for the tons of carbon dioxide per person or per capita. So we divide this value by 100%. So simply we get 7.5 tons of carbon dioxide on an average. So it means that on an average, one person of that apartment building produces or emits 7.5 tons of carbon dioxide. Very simple example, just to give us an idea that for different scenarios, it helps us to calculate the carbon footprint. And thus it helps us to find out the emission made by a specific group of people or an industry or anywhere. So it means that once we know the fuel intake or the fuel consumption, then we can easily find out how much carbon will be emitted by the burning or consumption of that fuel. So this is probably, yeah, this is the last example for calculation of the carbon footprint. So here we have an oil furnace. Again, the efficiency of the furnace is given, which is 80% efficiency. So we have oil furnace 80% efficient. It emits 20 millions of BTU of heat. So now the heat is given. So we have oil furnace. Previously it was gas furnace. So we have oil furnace. So we are injecting oil. So oil is actually burned by fire, flame of the fire. So you burn the oil and that produces 20 millions of BTU of heat. So here we have 20 millions BTU of heat being produced by the burning of the oil. And the oil furnace efficiency is 80%. The question is calculate the carbon footprint in tons. This value is given. So this is the value of heat generation per gallon of oil. So that means if you burn 1 gallon of oil, then it will produce 139.000 British thermal unit of heat. And then the conversion, then the carbon footprint for the oil itself is given. So it says that if you burn again 1 gallon of oil, it gives you 22 pounds of carbon dioxide. It releases 22 pounds of carbon dioxide. So the question is calculate the carbon footprint of this oil furnace in tons. Again, we know, again, let's calculate the input heat first. Okay, so that value oil furnace emits means this value of heat is at the output. When we say emission, this heat is at the output side. We know the efficiency, so we know the output heat, so we can easily calculate the input heat. So the input heat is simply output over efficiency. output heat is given as 20 MBTU, efficiency is given as 80%, so that is 0.8. That gives us the value of input heat as 25 millions of BTU. If you break it down, then it gives us in BTU, it is 25 into 10 to the power 6. Now, this much of heat is basically our produced at the input side by the burning of the oil. So if this much heat is produced, what is the amount of oil? How many gallons of oil will be required to produce this much of heat? So we know this value, 139.000 BTU per gallon. So if I convert it into gallons of oils from heat, so this is the input heat. This is the conversion factor from BTU to gallons. So BTU and BTU cancels out. That means we are actually at the input side of the oil furnace. This many gallons of oils is required to produce this much of heat. So this much of oil produces how much carbon dioxide? So for that, we need this value. So for 1 gallon, it produces 22 pounds. We have this many gallons. So how many pounds of carbon dioxide will be emitted? So this will be the value in pounds. So gallons and gallons will be cancelled out. But the value we need is in tons. So again, we need the conversion factor of 1/2000 that converts the pounds into tons. So we are left with 1.98 tons of carbon dioxide. So with this operation of oil furnace, we have 80% efficient oil furnace. It emits 20 millions of BTU of heat. Means if we know the efficiency of the machine, of course, from the manufacturer data, we will know the efficiency of the machine, of the furnace. So that is known beforehand. If we measure the heat, if the heat value can be measured, these two values here, the assumed values, are actually taken from some standard data. So these two are also known. So if we simply know the efficiency of the machine and we know the type of oil which is used, of course, that type of oil will determine this value as well as this value. So depending on the oil type, oil composition, these two values may change a bit. So if we know the type of the oil, that will determine this value and as well as this value. Know the efficiency of the furnace, we know the heat output of the system, then we can easily calculate the carbon footprint. So once we know the carbon footprint, then we need to limit the emission, or we need to get rid of the emission. So how to do it? What are the practices that are currently going on? So let us see at some of those practices. So now we come to the point that how to deal with these emissions actually. So let us see. There are some practices, and each practice has its own advantage and disadvantage. We are not going to go into too detail of these concepts. Just I'm going to give you the basic idea. So one of the practices or one of the instrument to limit the carbon emission is to introduce carbon pricing. And under carbon pricing, we have two practices, very well-known practices. The number one is the carbon tax. So let us see what is actually carbon tax. Carbon tax simply means when we use the fossil fuel. So what is carbon tax? So let's say an industry, we have an industry. It uses coal for its manufacturing, okay, manufacturing plant. So because the industry uses one fossil fuel, what the government will do to limit the emission, okay, the target is to limit the emission. So to limit the emission, what the government from the government side or the policymaker side, what they will do, they will charge, they will have, they will set a higher price on the coal. So the coal price will go high. Where will be the effect? So the industry has to pay more. So if the coal price gets high, the industry expense goes high. But of course, it will not run its business for introducing losses. So what it will do, the cost of the product, whatever product is being produced by this manufacturing plant, whatever product it produces, the cost of the product will go high. The consumers has to pay more. And here the effect will actually come. So when the consumers will see that, well, they are having to pay a bit more for buying this product, what they will do, some consumers or some customers will of course continue with the higher payment or larger cost of the product because they like the product very much. But some consumers will actually shift their interest from this product, and of course they will try and buy some other product. Okay. So once that happens, what the industry will think, when the consumers focus to some other products, they are actually losing consumers. So industry lose consumers. That means their profit. If this happens, the profit gets lessened. So what the industry will ultimately think, that what is the actual cause of the increment of the product cost? The actual cause is the introduction of carbon tax. So this was the cause basically for the rising of the product cost. So what the industry will then do, they will look for some alternate solution. Either they will limit their, what should I say, purchasing of the coal, or they will shift their focus from coal to some other renewables, which will again bring this cost of the product to its original price. So thus, by introducing the carbon tax, the government or the policymakers, energy policymakers, what they can do, they can actually discourage these industries which are currently run by the fossil fuels to shift their focus from the fossil fuel based production to more green energy or cleaner energy or renewable energy based production. So this is how carbon tax actually works. Now, of course, for each kind of fossil fuel, the amount of tax will vary. As we can see from the previous slide, this carbon tax actually varies from country to country as well as from fuel to fuel. Why? From fuel to fuel, variation is pretty clear. The price of or the carbon tax amount from fuel to fuel, you can easily see that for each of the fuel, a different amount of carbon emission happens, or the carbon, or in other words, we can say that for each of the fuel, the carbon footprint is different. So whenever the carbon tax is being set, they have to keep in mind, they actually, these things they keep in their mind that the fuels, the fossil fuels which emits larger amount of carbons should have a larger carbon tax and vice versa. So thus the policymakers or the government, they can limit the practice of using fossil fuels as the main fuel for running the industrial plants or offices or whatever. So the main theme is to discourage the business owners or the industry owners to shift from fossil fuel based plants to renewable energy based plants by increasing or by implementing or by incorporating a tax for the fossil fuels or the raw materials for generating energy for the industries. So this is more or less the concept of the carbon tax. So in this case, in the carbon tax, actually, there is no limit of emission. So in this case, the government, so when we talk about carbon tax, there is no limit being set by the government, no limit on the emission. Okay, the more they emit, that means basically government or whatever agency. So it means that an industry can use as much fossil fuel as they want, but of course, accordingly, they have to pay the carbon tax. So the more they use, that means the more fossil fuel they use, they buy from the market, the more they will emit the GHG or the carbon dioxide in the environment, and the more carbon tax they have to pay. So there is no limit basically on the emission itself. Okay, emission limit is not being imposed by the government. Now let's come to the second one of carbon pricing, which is the emission trading, or in other words, it is famously known as cap and trade. How does it work? So in the cap and trade, what happens? Very interesting scenario. Let's say we have two industries. This is industry one, and this is industry two. So this is industry A, this is industry B. What the government will do to limit the emission, carbon dioxide emission. So now let's say both of them, they are emitting some carbon dioxide. Okay. And of course, based on the size of the industry and the amount of fossil fuel being burnt or used up by the industries, the amount of emission will be there. And it can be easily calculated using the carbon footprint of the fuels of the industries. What the government will do, they will put a bar or a cap or a limit. So this is the cap, or we can say the maximum allowed limit, maximum allowable emission. So this is the maximum allowable emission that the government allows, or the environmental agency of the country allows. What they will do, these both of them will buy a certificate. So we say, let's say carbon certificate. Okay, both of them has its own carbon certificate. Now, the company B, let's say currently is producing this much, and the cap is being set to this value. Okay, it's producing a higher value of emission, and they were operating, and then the government put a bar or maximum limit or cap on the maximum emission limit for all the industries in a certain year. So talking about a year. Now, let's say this was also producing, but its production was a bit lesser than this. So what they both of them will do, both of them have their certificates, own certificates of using carbon or emitting carbon. That means they can emit a carbon, but the certificate says that, well, you can emit only up to this limit. Now, company A adopts a policy, which is a low-cost option. They find a low-cost option for limiting their emission well below the cap. Let me draw it again. So this is the cap, and they find an option. Which allows them to limit their emission well below the allowed limit or well below the cap set by the government. So originally they were producing more. However, they find a low cost policy. They have some policy of their own to limit their own emission. Company B fails to find such policy. For limiting this carbon emission. Okay, they try to find it, but however, for whatever fuel they had, whatever infrastructure that they had, probably they didn't find, or they couldn't find any policy which allows them to limit their emission at least at this maximum level. So they have an option, they found an option, but that option is very costly option. That means they can limit the emission, of course, but that will cost them more. So what they do, they seek help from company A. They say, well, they make an agreement. Give me your carbon certificate, your carbon credit. We call it carbon credit, basically. This is the carbon credit. Or we call it carbon credit certificate. You sell this much of available, this much credit to me. Okay, so they ask for this much of credit. So they seek help from company A. Company A agrees to sell this much of available carbon credit to company B, sells. So the carbon credits is sold to company B at a price. Now, because this is a mutual agreement, the selling price which is of course profitable, shouldn't say beneficial, it's profitable. For A, as well as the price is profitable for B. How is that possible? Remember, B was also trying, at the very beginning, B was also trying to limit its emission by following some policy, but it was unable to find a low cost policy. Okay, thus it was emitting more beyond the maximum allowable limit by the government. So what they will do, let's say the price that they found here, let's say, for example, $50, okay, per ton of carbon dioxide emission. So if they were looking for implementing this policy, it was a high cost option. Now, when they buy it from A, probably A agrees at a price, let's say $35 per ton. Okay, so A sells the permission, and the rate is set at some equivalent $35 per ton carbon dioxide. So now what that means, this additional amount is shifted here, and probably that will make the cap of industry B higher. Okay, so initial cap set by the government was here. Government sold the carbon credit to each of the industries. Industries tried initially to keep their emission well below the cap, or at least at the maximum limit. Industry A got some low cost policy. So they limited their emission well below the cap. So they had some credits available, carbon credits available. They sold it to company B. So now company B can emit a bit higher carbon dioxide, but at a lower cost. Okay, so that's what we can see, that the cap is actually maintained. The cap is actually maintained, and the money flow, the cash flow, is also economical for both sides. So A is becoming winner by selling the extra additional carbon credit to B. B is becoming winner in a sense that it is now adopting a policy which is costing it less. Overall, the government is the winner because the cap that it established is maintained. So everyone is a winner. Of course, there is a negotiation. So this negotiation uh, is a very critical issue because in this case, of course, company A has to agree to sell the carbon credit at a pretty lower price so that company B agrees to buy it from them. If not, then probably company B will go to another company, let's say C, another industry who is willing to sell the carbon credit at a lower price. So of course, I am showing the only two players in the scenario, but of course, there are many, many industries in this scenario, many, many players in this scenario. Now, I talked about the cap for a certain year and a consecutive year. In the next year, what the government will do, they will impose a lower cap. They will declare a lower cap with an aim to reduce the overall emission. Then the same scenario, the same policy will go on and on and on. And ultimately, it is hoped that the companies will be able to run with no emission at all. So this is about the emission trading or cap and trade policy for limiting carbon emission for the industries. Okay, so in this case, what is happening? In the first case, in the carbon tax, the government didn't set any limit on the carbon emission, but it was simply setting a price for the fuels, higher price for the fuels. And thus setting a higher price, it tried to limit the emission. So the price was set by the government or by the policymaker. Emission was not set by the policymaker. In the second case, emission trading, the emission limit was set by the policymaker or the government. The price was actually mutually agreed upon by the players in the market, in the carbon market. So this is another basic difference between carbon tax and emission trading. Now, again, there are different policies other than carbon pricing. If we talk about decarbonization, it's the same thing as the limiting the carbon emission in the environment, the same thing. There are two ways again. One, we call it carbon neutral. Another one is net zero carbon. What is carbon neutral and what is net zero carbon? Let us see. In the carbon neutral scenario, so basically decarbonization means we are trying to capture the carbon or limit the carbon emission, we are trying to make the environment carbon free, carbon dioxide free or carbon free. So in the carbon neutral case, let's say we talk about an industry again. So the industry, again, let's say this is industry A. So it is emitting some carbon into the environment. Now they say they are carbon neutral. They claim that they are carbon neutral. How that is possible? What does that mean actually? So when someone says we are carbon neutral, what does that mean? So what they actually do, they know they have their carbon footprint being calculated. They have the expert, they calculate their carbon footprint. And first of all, they try to limit their emission. So in the carbon neutral, the first step is to calculate the carbon footprint. Next step is to adopt some policy. And whatever is left, so by limiting, it means that the carbon emission has not been achieved altogether. Okay. So that means if, for example, they were emitting 50 tons of carbon dioxide, okay, per day, let's say per day, they adopt some policy to limit the carbon emission. And after adopting the policy, let's say it came up to 25 tons of carbon dioxide per day. And then that means in their policy, their target was actually not to completely eliminate the carbon emission. So whatever was their supply chain or whatever processes or industrial plants they were using, still, okay, still they are using the fuels which emits carbon dioxide, but they limited it to half of it, half of the original emission. What about the remaining? The remaining emission, what they will say we invest. So they will invest in projects which are not run by, which are not owned by the owner of this industry. Okay. So they will invest in green projects. So invest in projects which are green in nature, such as reforestation. So they will look for reforestation, planting trees, green energy initiatives, and other such things. Okay. So they will fund in the projects where the environmental, let's say, they will fund in some projects where the cleanliness of the ocean or the healthiness of the ocean will be monitored, the healthiness of the rivers or whatever water bodies are there will be monitored, and there will be some works going on for the betterment of the water quality, for the betterment of the air quality, and so on. So when they will invest in the reforestation project, what will happen? The trees that will be planted, they will be starting to actually capture the carbons. So these are the natural processes. Okay, these are the natural processes. Reforestation is a natural process. Green energy initiatives. So wherever people are trying to implement, or any company is trying to produce, any company is producing, let's say, wind turbine or solar panels or biomass based energy production system or waste to energy conversion system. So this industry A will invest there, okay, in the green energy initiatives or green energy introduction into the society. So thus this is an indirect approach. Okay, they themselves may not or will not actually eliminate altogether the 50 ton of carbon dioxide. They may not even make it half of it. Okay, although I said maybe they will adopt some policy to make it half, reduce it. It may also happen that they are not actually changing their overall manufacturing system at all. So the original 50 ton of carbon dioxide per day is still emitted, but what they are doing, so that means maybe they will not go for this step. Directly, they will calculate their carbon footprint and they will claim that whatever harm they are causing to the environment, indirectly, they are actually eliminating that 50 tons by investing in the green projects. So this is what is meant by carbon neutrality. So if this is 50 tons of carbon dioxide, what they will do, they will eliminate this 50 ton altogether, with a claim that with their investment, probably they will also calculate the carbon footprint of this reforestation. In this case, the carbon footprint will be negative, of course. Okay, for reforestation, the carbon footprint will become negative. That means the forestry or the planet or the plants that they will plant through the projects will actually capture the carbons. So that means instead of producing positive carbon, emitting carbon into the system, they will actually capture the carbon naturally. Another way to, there are actually many other ways. like we call it in general carbon sequestration. This is another process where carbon is actually captured, not natured. So reforestation is basically one way of carbon sequestration. That means you capture the carbon and you store it somewhere. In the natural process, we go for reforestation. There are other processes which are not natural, where actually the carbon is captured from the air and it is actually stored underground. So that is a man-made process of carbon sequestration, you can say. So this is how the carbon neutrality can be ensured. Remember, here they did not actually changed their production or manufacturing plants at all. If they change it a bit, if they try and incorporate some policies which can reduce the carbon dioxide emission from 50 to 25, that means the investment here will be less. Of course, if they don't invest here, that means if they don't adopt step number 2, then of course the all investment should come here to compensate this much of 50 tons of carbon dioxide emission. So they're not changing their regular practices of emitting 50 tons of carbon dioxide. Indirectly, they are saying that, well, we are investing the money somewhere else, and that will actually neutralize this 50 ton of carbon dioxide emission into the environment. The next one is net zero carbon. This is another way of decarbonization. So in the net zero case, we can say this is the larger target. It is the larger target. And it is a bit more difficult and time consuming, okay? A bit more difficult as well as time consuming. What it does is this. In this case, they change their policy. They change the same industry A, they were emitting 50 tons of carbon dioxide per day, let's say. The same industry, they changed their policy. By changing their policy, it could be that they have actually changed their overall production chain, okay? Overall production chain or supply chain or value chain, whatever you say. So they changed their policy of manufacturing. Maybe they are going for completely green energy input to their system. So maybe they are introducing solar cell, they are introducing wind energy, maybe they are introducing the hydro energy, they have some dam available, river available nearby, maybe they have some ocean nearby, they are going for the wave energy or tidal energy, maybe they are using their industrial wastes and converting it to energy, and so on. So they are actually changing their old practices, which were emitting 50 ton of carbon dioxide per day. And by changing their policy of manufacturing and other practices of their value chain, their transmission and distribution of the products, okay, and so on. So they're changing their complete practices, complete industrial production process is changed, updated to actually limit this 50 ton. Okay. And when they do so, probably they will come up with maybe in their carbon footprint, because in their carbon footprint, maybe they will come up to very small value of 5 tons of carbon dioxide per day. And then they will go for carbon sequestration. And thus they will claim that the net zero carbon scenario is achieved. So the major difference between carbon neutral and net zero carbon is this. In the carbon neutral process, the industries are not willing basically to change their manufacturing process altogether. Rather, they're investing it somewhere. The money is invested for some green projects or carbon sequestration projects. Whereas for the net zero carbon, the industry is willing to change their overall manufacturing process, and thus they can limit it to a very small value where a very small investment may be required to get these 5 tons of carbon dioxide per day eliminated altogether. So because here in this case for the net zero carbon scenario, it requires the industries to change their setup altogether. So basically it will take some time. So longer period of time is required in this case, whereas for carbon neutral, it can be implemented in a very short period of time, comparatively shorter period of time. Then we go for 2 more concepts. One is the net zero emission. And another one is the climate positive. So what is net zero emission? Here we talked about net zero carbon. Look at the differences. This is net zero carbon. So in the net zero carbon, the major target is to eliminate the carbon emission only, whereas in the net zero emission, we consider all sorts of emission, not only carbon dioxide, but other than carbon dioxide, all other sorts of greenhouse gases emission should be compensated through this approach. So the only difference here is in the net zero carbon, we talk about the emission of the carbon dioxide, which goes under the decarbonization topic. Whereas in the net zero emission, we talk about the emission, we talk about the elimination of all kind of GHGs altogether. And what is climate positive? Another term which says that now in the net zero carbon or carbon neutral, what we said? We said if there is 50 tons of carbon dioxide, then emitted, we should do something to get rid of this 50 ton of carbon dioxide. So climate positive, on the other hand, says, well, you adopt some policies where you produce something which captures carbon further, or so here you produced 50, you eliminated 50. So this 50 was because of our own actions. Okay, household activities, industrial activities, office activities, and so on. So we produced it additionally. It was not available in the environment at the beginning. So whatever we produced additionally, we emitted in the environment. We are doing something, adopting some policy, changing our lifestyle to get rid of these 50. But remember, it's still without our activities, even we do not use fossil fuel, we use all the green alternatives, we achieve net zero carbon, we achieve net zero emission, it's still in the environment, there will be some carbon, there will be some carbon dioxide naturally available. So this is naturally available carbon dioxide. And we further go one step forward. This is net zero, we achieve net zero. All the carbon dioxide, emitted carbon dioxide were compensated, absorbed, and we got rid of all those carbon dioxide. Now we invest or we adopt some other policies to capture the natural carbon dioxide or whatever carbon dioxide was not produced by us. So that carbon dioxide, if we can adopt such policies, then we call it as climate positive, or another word is carbon negative. That means our policy is such that if we produce 50 by our activities, let's say the policy is such that it can get rid of 60 tons of carbon dioxide per day, which will make the overall carbon in the environment negative. So this is known as climate positive or carbon negative. Okay, so these were some of the keywords and terms associated with the emissions. And now with this small description of all these, we are probably done with the intro of the renewable energy part. We gave some statistical data, some world maps of resource availability, some statistics of different kinds of fuels, uh, definition of renewables and sustainables and types of energy sources and so on. So at the end of the slide, and today's class, we have talked about a bit about the carbon footprint calculation and some very common terminologies which are practiced in by the environmentalists or by the environmental engineers when they talk about emissions. So before we end, let's go quickly through some basic working principles or the basic working principles of some of the renewable energy resources. So to start with, we talk about the solar PV. Basically, we expect light energy. We have a PV cell. So solar PV is nothing but the solar photovoltaics. So means we are, so this PV stands for photovoltaics. Means we absorb photon. Photon energy or light energy, and from using that light energy, using the energy conversion mechanism available in the solar solar cell or PV cell, we expect voltage. So here in this case, the electricity generation takes place. Basically, we have the light energy and we have a sandwiched N-type silicon and P-type silicon. The N-type silicon is usually situated at the top and the P-type silicon is situated at the bottom. The N-type silicon, the width or depth, this width is much, much less. So if I say the height of the N-type and this is height of the P-type, then height of the N-type silicon is much, much less than height of the P-type silicon. Why this is done? So although in this diagram, it shows that they are almost comparable, almost identical, but in practice, the height of the N-type silicon is much smaller than the P-type silicon. This is just to allow the light energy to go through the thinner N-type silicon quickly to the depletion region. So remember, we have a depletion region here, just beside the junction, PN junction. So I hope you understand what is meant by N-type silicon and what is P-type silicon. Basically, silicon, in the silicon, which is an intrinsic semiconductor, we dope phosphorus or group 15. So silicon is basically group 14. Okay. Then if we have group 13 and we have group 15. So in the silicon, we have 4 outermost electrons. In the outermost shell, we have 4 electrons. And in the phosphorus, we have 5 electrons. So we have 1 additional electron, and we have boron, which is 5, whose atomic number is 5. So we have 3. So in the outer shell, we have 1 less. If it is 4, then it is completed. In this case, it is 4. Okay, 2, 8, and 4. This is 2 and 3. And this is 2, 8, and 5. So we have 1 extra here in the phosphorus case. So for making N-type silicon, what we basically do, we dope the phosphorus into the silicon. So there is doping. So we dope by phosphorus. And here in this case, for producing P-type silicon, we dope with the boron. Thus, in the P-type silicon, we have many holes available. In the P-type semiconductor or silicon, we have, in the N-type silicon, we have many free electrons available. So once those free electrons and free holes available in these two kind of materials, these two kind of N-type and P-type semiconductors. Once they are sandwiched, the electron and holes, they actually recombine. These things are actually covered in your earlier course. I'm just giving you a little review. And once those recombine, you have some barrier potential or some depletion region. In the depletion region, we have charge neutrality. Okay, rather we have positive ion and negative ion, but we do not have any free electrons or holes. So if we say, so this is about the depletion region, just nearby the nearing the junction. So when the light energy falls upon this junction, additional electron and hole pair is generated. Why? Because when an atom accepts additional energy, the electrons gets excited and they try to move to the next higher energy level. So they try to move into the next higher energy level. So if, let's say, this is an outermost electron, let's say, for example, if true electron, let's say, just for an example. So each of these shell, this is the innermost shell, this is the second one, and let's say this is the outermost shell. Now each of these electrons are bound to its valence band. So when light energy falls upon it, so this is H nu, when light energy falls upon it, the electron absorbs the energy and gets agitated and would like to become free. Okay, remember, this electron is actually moving, it is present in this outermost shell and it is containing some energy level. That is the potential energy. It is not moving, so it is the potential energy. Can be calculated. Now, when the light energy or photon energy comes and the electron absorbs it, so it jumps out of it. So let me make it this. So this is our innermost one. So these are the electrons. So upon absorbing the light energy, this electron is agitated or excited and it becomes free. So now you have free electrons and it leaves behind a hole. So thus electron hole pair is produced. So here you can see these electron hole pairs actually is shown in this manner. So we have electrons hole pair produced, electron hole pairs produced. So the minus ones are actually represented. These are the representative of the electrons and the plus ones are representative of the holes. And then you have the two electrodes. This is the positive electrode and this is the positive electrode and this is the negative electrode. Electrons and these electrons now gets drifted due to the production of the electric field. Remember that, okay, let me draw it. Let me draw the scenario. So, so let's say this is my N-type, thin N-type, and this is the junction. This is the P-type. So this is the P-type, full of holes. This is the N-type, full of electrons. We have some metallic contacts. The top metallic contacts are discontinuous, rather they look like fingers. In the 3D view, they will look like fingers. Here I'm just showing the metallic contacts from the 2D viewpoint. So let's say 3 metallic contacts and the lower one, solid one. So a solid metallic contact at the bottom and some finger type discrete metallic channels are being created at the top. One reason, because we want the photons to come and penetrate through the N-type region to the junction. Okay, this is the junction, and this is basically the depletion region. This is basically the depletion region. And in the depletion region, you have the electric field being created. So you have many electrons here. And you have many holes here. Of course, these are the majority carriers. Besides these, we all know that there are some minority carriers also. So to begin with, of course, when we sandwich them, okay, when we create the PN junction, single crystal PN junction, then what happens? Okay, so here you had the negative. Remember, at the very beginning, this junction was not there. So these were part of electrons and holes, electrons and holes, electrons and holes, electrons and holes. Okay, so these were the cases. So near the junction, so this is the junction. This is the junction, PN type. So near the hole, near the junction, what happens? Because of their concentration, there will be some diffusion. So here in the N type, there is larger amount of electrons. Here we have very small number of minority carriers. So due to the diffusion process, what these electrons will do, they will come and cross the junction and they will recombine with the holes. So that means what? We have electron hole recombination, and there will be a certain region just nearing the junction where you have some, where the space will be devoid of any sort of free electrons or holes. So because electron gets eliminated from here, what will happen? We have one less electron. Electron is recombined. So if we update the diagram, let's update it. So there will be space nearing the junction because of the recombination. You remember electron got lost, it got recombined. So you have some positive ions. And you have some negative ions. So you can clearly see that now we have no free electrons and holes available in this space, and we call it charge depletion zone or depletion region. And an electric field is established. An electric field is established because of this positive ion and negative ion. So, and because of this depletion region, basically the hole, when they will try to diffuse over to the N region, they will be repelled by these positive charges, positive ions. Similarly, the electrons, when they will try and penetrate to this P side of the junction, these negative ions will actually repel those electrons. Thus, there will be an equilibrium and a depletion region will be established. So we have an electric field now. And this electric field, when this the light energy will come and it will go through the N-type material and hit this junction. So now from these positive ions, the additional electrons, this thing will happen. So H nu will be captured, some more free electrons and hole will be created. These holes and electrons, so remember that now we have with the photon energy H nu, some electron and hole will be created. And with the presence of this E, what will happen? You will have this direction of electron flow. So if we give a path for the electron and hole to flow, so we call it the negative electrode. Because why? Because based on this electric field present in the depletion region, the electrons gets now attracted in this direction, the free electrons, and holes gets attracted in this direction. So we have a positive electrode at the top, so negative electrode at the top and positive electrode at the bottom. Ultimately, you have a closed circuit. If you close the circuit by a load, then you will see that the electron flow will be happening in this direction. And we all know that the current direction we always take as the reverse direction of the electron flow. So this is the flow of electron out of the PN junction. Due to the incidence of light energy, electrons gets agitated. They become free electron and they leave behind a hole. So there is electron hole pair generation. Because of the presence of this electric field now, the electron will get the direction of flow like this, and the hole will follow in opposite direction, and the current direction will be the same as the hole direction. So this is the current direction. So now the energy that is received by this electron, the energy of this incident light has to be enough to release this electron. Okay. So whatever energy is required, let's say if it is, for example, 1.5 electron volt of energy is required for this electron to be attached with the atom, then the H nu has to be higher than 1.5 electron volt to release this electron. So this is how basically the solar PV concept works. With respect to a conventional PV junction diode, okay, this is the construction wise it is a bit different than the conventional PN junction diode. One difference is regarding the thickness of the layers. In the conventional PN junction diode, the thickness of the N layer as well as the P layer are all exactly same, exactly identical. However, in this case, for the solar cell, solar photovoltaics, the thickness of the N layer is intentionally kept smaller, thinner than the P type. Another difference is the surface area. Okay, the surface area of the solar photovoltaic or the solar cells are comparatively larger compared to the conventional PV cells. The conventional PN junction diodes. Why? Because we want to allow more sunlight to be captured by our PV cell. So if more sunlight is available, more energy will be available and more electricity can be generated. So these are the two basic differences between a conventional PV junction diode and our solar cell. Further detail will be given when we will take the topic of solar PV cell in detail in our coming classes, future classes. So now let us go to the second kind of renewable energy generation process. So the second one is basically the wind energy. So in this case, the energy conversion process is basically from light energy to electricity. The second one is the wind energy production from wind turbine. So basically, this is a schematic. These are the rotor blades, very large rotor blades. Then these arrows are representing the wind direction of the wind. So when wind comes in and hits the rotor blades, the rotor blade starts to rotate. So when the rotor blade starts to rotate, there is a certain speed. There is a certain speed, of course. So we have a speed in a certain direction. And of course, we have a certain amount of torque. So when there is movement of the blade in this direction, so it will produce a torque at this point. And we have a gearbox. So the wind basically rotates the wind turbine blades. We have a gearbox being attached to the rotating part of the wind blades. Okay, at the center of the wind blade, we call it this extended part. We call it the rotor hub. So the rotor hub is basically connected to a gearbox. The job of the gearbox is to convert these low speed of the wind blade to a higher speed of higher shaft speed at the output of the gearbox. So the gearbox input speed is low. So gearbox input speed is low, whereas the output of the gearbox is pretty high. And the teeth number of the gearbox is designed or chosen appropriately accordingly. We need higher speed at the output of the gearbox because the machine, the device that we are using here, the generator, the mechanical torque is being produced by the wind. So the kinetic energy of the wind comes in and it produces the mechanical energy. So the input to the generator is mechanical and output of the generator is electrical, as we all know. Now the type of so when the wind comes, the kinetic energy is converted into mechanical energy. Mechanical energy is converted into electrical output, and that electrical output is taken down through the tower, tall body of tower, through the power cables, and then the transformer is used to step up the voltage so that it can be supplied to the grid consumers. So this is in short the operating principle. Now the type of generator and the other associated accessories will differ from one type to another type of wind turbine generation scheme. So there are a good number of connection scheme of wind turbine generator. We will again discuss it in detail when we come to the discussion of wind turbine generation, wind energy generation in some later slides. The next one is hydroelectricity. Simply we have to set a dam. In this case, the purpose of setting the dam is to create some potential energy available from the water or hydro resources. So when we produce the dam, let's say initially or previously, this was a river. This was a river of this height. So what they do, first of all, they create a dam. And that actually hampers the aquatic life of the river, aquatic life of the inhabitants of the river actually. So what happens because of the creation of this dam, one side of the water level rises and we call it the reservoir, other side of the water level goes down. And this dam, because of this dam, we have a water height. So this is the water height, H. We have the mass of the water available, water mass, MW, height of the water, and then we have the gravity of the water. So basically, within this reservoir, we have some stored potential energy, mgh. There is a sluice gate which controls the flow of the water from the reservoir through the penstock, which goes through the dam. It's a long pipe kind of structure, and that allows the water to have a certain amount of velocity. So of course, if the mgh is higher, the h is higher. So if h gets higher, you have higher amount of potential energy that will give you higher amount of kinetic energy when you open the gate or the sluice gate. This is the sluice gate. When you open it, then it allows water to come through it, through the penstock, and that rotates the turbine blades. So this is your hydro turbine. So this is the hydro turbine. So the turbine blade rotates, and once the water energy is used up, then the water actually flows through this channel and goes into the river. And then whenever you have the turbine blades gets rotated, that is coupled to the generator shaft, and then the generator, the synchronous generator, it will produce the three-phase power, and then again you take it to your transformer, and transformer will take it to the remaining part of the grid. So thus you can have the hydroelectricity produced by creating either some uh, artificial dam, or there may be some natural dam which are already there. You can use it. You can have a reservoir being designed there, so that you can have some MGH, and that will be converted into the kinetic energy, which will run the rotor blade, and ultimately that will be converted to electricity. So this is about hydroelectricity, and let's now move on to another kind of renewable energy, which is the biomass. And probably after this, we have geothermal. Okay, so let's move through this quickly. So in the biomass energy, what we do, simply, very short, we have the sources of biomass. And if you closely look at this, the type of the biomass is like the tree logs of the trees, some food corns, some industrial residues or industrial wastes, uh, the sewerage waste or the sewerage resources, the waste, municipality wastes, as well as the household wastes. So these are some of the input feedstock for the biomass-based generation. Whatever is the type of resource, what we do, we simply use it, we process it, and we use them for producing steam. Okay, we burn them and we produce steam. That steam actually, yeah, so from the water we produce the steam. So that steam is actually used by the turbine for getting the rotation. So basically, these resources are actually burned over here. These resources are burned over here. We have some water reservoir. From these water reservoir, we pump the water. So to start with, we pump the water. This pumped water goes through this heat chamber, where these biomass-based resources are being burned. Heat energy is produced. So we can also call it a heat exchanger. So this heat actually heats up the cooler water and turns the water into steam. And this, once the heat, so the remaining exhaust gases are actually taken up by the chimney, and that goes into the environment. So then this steam is actually used up to run the turbine. Once the turbine is rotated, that rotates the generator again, and that actually produces the electricity, which is then transformed with the use of the power transformer to power up the consumers. The steam then gets cooled down by some condensation, natural condensation, or condensation process, artificial condensation process. And then after releasing the heat of the steam, it gets condensed and converts into water again. That water is again pumped with the feed water pump through the heat chamber, and like this, the cycle continues. Of course, this is a very, what should I say, trivial process being shown here. Much more complexities are involved in the biomass, and much more steps are actually, terminologies are also associated with the electricity generation process. Now the question is, in our one of the earlier discussion, we treated this biomass energy as unclean source of energy. Now there is a debate with this. Some says that, well, so you are producing electricity, so you are in a sense releasing or emitting harmful gases into the environment, as seen clearly from this production process. But those who are against this, those who claim that, well, biomass is still a clean energy, what is their logic? They say that whatever resources that we are using for producing the biomass-based electricity, those were already in the environment. Those were already part of the environment. So whatever carbon dioxide we are talking about, you see, each of these have its own carbon content. Okay. So, so not very long ago, these were part of the environment. And we are simply burning them and releasing those stored carbons into the atmosphere. So they were part of the environment, maybe 1 week ago, or 1 day ago, or maybe 1 month ago. So those were part of the environment, and we are releasing it into the environment. This is completely different compared to the conventional energy resources, which are called as the fossil fuels. Where is the difference? The fossil fuel based carbons, or the carbons stored within the fossil fuels, were not part of the environment 1 month ago, or 1 year ago, or maybe 1 day ago. They were stored underneath the ground, and millions of years passed by before those were formed. Like the coal was formed, the oil was formed, the natural gas was formed. So those carbons got accumulated for many years, millions of years. So they were not the immediate inhabitant of the environment. Those carbons were not the immediate inhabitant of the environment. Rather, they used to be in the environment millions of years ago. So they were suddenly, when we burn those fossil fuels, they are suddenly gets released into the environment and increases the overall carbon dioxide content in the environment. Whereas these biomass-based resources, maybe these were available in the nature, they are stored not so long ago. So they were part of the environment maybe 1 month ago, or 1 week ago, or so on. So in that sense, some people claim that biomass is still a clean energy source. It is not as unclean as the fossil fuels, because the fossil fuels were they were not there, okay, in the immediate past. Of course, they were there millions of years ago. They got stored under the earth's surface, but the storage time was long time. Millions of years ago, they were part of the environment. But now suddenly, when we extract them, when they extract those fossil fuels, we burn them, suddenly they increase the amount of carbon in the environment. And whereas these biomass sources, they were part of the environment not so long ago, and we are simply burning them. And another thing what they say, that, well, we are using this crop type of things, with this tree type of things. And of course, for producing more biomass-based fuel, we have to plant these trees to get the corns regenerated. We have to plant again these trees again to get these tree logs available for biomass-based energy production. So this is another way they defend their logic, that the biomass, although they emit carbon dioxide, we, as a biomass energy producer, we have to plant these trees. We have to plant these trees to get the continuous supply of this kind of biomass-based fuel. So these are their logics. So there is a debate that whether the biomass is a clean energy or not. Some say it's clean, some say it's not clean. And each of them has their own logics. So the last one is the geothermal electricity generation. Here, we use the heat energy available under the earth, where the earth center it contains a temperature around 6,000 degrees Celsius. And as we move away from the earth center, there's a temperature gradient. There's a temperature gradient, of course. So the earth center gives you 6,000 degrees Celsius. As we move closer to the earth's surface, the temperature reduces. However, still the temperature is pretty high, maybe a few kilometers from the surface of the earth. So if this is the surface of the earth, maybe within few kilometers, you will get some very hot body of, we call it magma. So tremendous heat is available there. So what they do, first of all, they have to find out if we are planning to produce electricity using geothermal energy available underneath the earth's surface. So what they do, they have to find out the existence of this sort of magma or magma where you have pretty high temperature. They inject water, cool water, through some well. So they have to dig some wells very near to that magma point. And those cool water, when it gets closer to this magma body, it gets heat up and it produces hot water. So the cool water is converted into hot water. These hot water, so we call these well through which we actually put water into or near to the magma body. We inject water, okay, from the top of the earth surface to the bottom of the earth surface. And these kind of wells, we call them injection wells because we inject water, cool water through these wells. It gets closer to the magma body. The heat takes the heat of the magma, and thus the hot water is actually taken up. Remember, this is done forcefully. So this injection is done forcefully through the pump. And then there is a closed path like this, another well or few well. Here only one well is shown, but there could be many wells. So this is the production well. This is injection well. And this channel is known as the production well. So through the production well, the steam is generated. So you have the steam generator. Once the steam is generated, that steam runs the turbine. Turbine is coupled to the generator shaft. Generator rotates, and ultimately electricity is being produced. The exhaust steam or the unused steam actually taken out through this channel, condensed inside the cooling tower, and then you have the cool water again coming back to the injection well. So this is the closed cycle of the geothermal energy production in very short manner. I have tried to give you the idea here. So that ends the presentation of this first slide, whose title was the Intro to Renewable Energy. If you are further interested in any single kind of these energy sources, in our course, mostly we will focus on the solar PV electricity generation, its design, and its detailed description, as well as the wind-based electricity generation. If time permits, I don't know whether the time will permit or not, then probably we'll look into the hydroelectricity and the biomass also. So that's it for today. I will share this slide with you and also the video recording with you. Please complete this video. Please listen to this video carefully. If you have any question, I will take those questions at the beginning of the next class. And if you have no question, of course, then we'll move on to the next slide, inshallah. Okay, so thank you very much. See you in the next class. Assalamu alaikum.